All right, today we're reviewing the learning objectives associated with forces, dynamics, continued forces, vectors, and moments. The first learning objective along with this concept was add two or more co-planar forces. So in the same plane, like X, Y plane, like this chalkboard, this is X, and vertical is Y. Here are two forces. Force 1, which is 15 newtons, directed 35 degrees above horizontal. And then force 2 is 10 newtons, and it is entirely horizontal. So they're in the same plane, right? And they're just two forces, so we're going to practice adding them. The way that we've kind of set it up to solve here is to resolve this force vector into its perpendicular components, kind of a preview of the subsequent learning objective yet to come. And so we may recall that if this force here is like the hypotenuse, we can construct legs of a right triangle, sort of like this and like this. Now these vectors here are the same as like this vertical component here and this horizontal component here. So these vectors are one and the same, and these vectors are one and the same. You can construct a figure that's convenient to work with. Okay, however you prefer to think about this. If you want to, sort of, here's my vector, and so I'm going to calculate the horizontal component down here. So this is adjacent to this 35-degree angle, but it's easy to see that this x component of force 1 is equal to the cosine of 35 degrees times 15 newtons. Right? Because cosine is adjacent over hypotenuse. And so if you multiply both sides by the hypotenuse, you can solve for the adjacent side like this. Remember, one of the ways that we mentioned to add vectors is with this quadrilateral method, where you can think about this force right here, and you can write both of the vectors sort of tail to tail like this. And so you kind of think about this was our sum, right? This is our resultant. So it's like a squared plus b squared equals c squared, but we could write those like this, tail to tail, and then that diagonal is the hypotenuse. And so again, you can translate a vector anywhere in space. The important thing about this y component is that it points up, and the magnitude of it, sort of like the height of it. And I can draw that anywhere sort of in space that's convenient. Sometimes it's convenient to draw some figure or we want. So this vertical component then is opposite the 35-degree angle, or it would be adjacent to this 55 degrees, right? It would be adjacent to this 55-degree angle. And so the vertical component is either, and let's prove this to ourselves in our calculator for right now. The vertical component you can think about as either the sine of 35 degrees times 15 newtons. But if what I just said is true, then the cosine of 55 degrees times 15 newtons should also be that, right? Because I prefer to work with this complementary angle and draw my legs over here because it's easier to sort of see them. And you see how they're both mathematically identical. So the more sort of tools that you have in the tool belt, the shorter work you can make with the draw. What's cosine 55 times 15 newtons? This side of the room. This side of the room is what we're going to get Paul on that. What's cosine 55 times 15 newtons? Or e-learners, I need your mic, type it in the chat. 8.6. This side of the room, what's the sine of 35 times 15 newtons? 8.6. They didn't need to calculate it. They just knew it was going to be the same. They just copied your answer. You did it, okay? And again, so it's going to be the same thing. So the angle theta, right, the function that we're doing, the sine or cosine, is going to be like the same as 90 minus theta, the complement, and the opposite sort of trig function, right? So in other words, if the sine of 35 degrees times 15 gives us that 8.6, then the cosine of its complement gives us the same thing. I was saying no, I was on you. I was just seeing if you could like read my lips through my face shield and my mask. All right. If there's a fire drill, I'll bring the E-learners with me, okay? I'm not going to leave you in here inside because if it's a real fire, right? That wouldn't be good. You're going to say, what's down here? Ah. Now I'm still recording because I think the whole. Yeah, we're still recording. Let's see what happens there when we go to play that back. We'll fill it. All right, so we said this was 8.6 newtons. No, we didn't. We said this was 8.6 newtons. The upbeat one. 8.6 newtons. How about the to the right component of this force one vector? So what is cosine 35 times 15? Say again? 12.3 newtons. And so if we wanted to get the resultant here, that would connect force 1 and force 2, the tail of force 1 to the head of force 2, and that's going to be the resultant. Let's redraw that resultant over here. And we know to have an x component equal to 10 newtons plus 12.3 newtons. Does that make sense to everybody where I'm getting these values from for the x, right? So we have a net x force of the 12.3 from force 1 and the 10 from force 2, right? So you're just sort of saying all the x's gives me the net x. All the y's, which was just this component of force 1, gives you the net y. But you can see, like, what if this one were also up at an angle, right? Then we have to resolve this one too. Sum of all the x's plus sum of all the y's. New right triangle, and then Pythagoras' theorem will calculate that. And so we want 22.3 squared plus 8.6 squared, and then take the square root of that sum of those squares, and that should be r. Let me get my calculator, and I'll erase you. That's no good anymore. We started doing everything. Calculator. All right. Ready, set, go. 22.3 squared plus 8.6 squared equals square root. All right, anybody else got it? What did you get at home? Leave it down in the comments below. So my youngest son, he watches a lot of YouTube, you guys. Like he watches, that's like his favorite thing to do in the world. And I just, by being around him, I'll end up, sort of being exposed to all this craziness. And I always hear like the same things, they're like, hey, you guys, turn your phone sideways, and if that subscribe button is red, make sure you turn it gray. I think that is. So he watches people like blogger Jews, some guys know who blogger Jews is, but kind of blend the thing there. Or Chad Wildplay, okay? Chad Wildplay, spy ninjas, that's like his favorite. A lot of time. All right, what do we get for a result? Anybody? 23.9 newtons. Let's calculate this angle theta. So this is the angle that R is making, okay? And then we could say relative to the horizontal, okay? The same way that we sort of oriented this angle force 1. So we can solve for this using the tangent function or the sine function or the cosine function because we know everything sort of about this right triangle. We know all the sides. I always like the tangent function. So the inverse tangent of opposite over adjacent, right, 23.3, solves for the angle theta, right? So we've got 8.6 over 22.3 gives me a ratio of sides opposite to adjacent, and the inverse tangent of that solves for the angle theta, 21 degrees. So it sounds like a really tough question if you said, hey, what is the sum of two coplanar forces, one force 15 newtons oriented at 35 degrees above horizontal, plus another 10 Newton force directed entirely horizontally? Where you go, oh, that would be 23.9 newtons, 21 degrees above horizontal. That would be the vector sum. It's hard to realize that, okay, without having to sort of know how to do the calculation. But while upon inspection, we can just kind of draw some vectors. We kind of have an idea about what the vectors, like we kind of know what's going up in this way. We kind of have a feel for, what the angle is going to be. And so when we're done calculating, we say, is this reasonable? Does this sort of match what my intuition, my sort of initial working suggested it should be? So resolve the force into perpendicular components. We already kind of did that. Let's just sort of recap and have a good sort of general figure here. If we have a force at some angle theta, we resolve it into perpendicular components using our trig definitions. And so the vertical component, the force vertical, or the force in the y direction if you prefer, is going to be equal to the sine of theta times the force. I'm going to rewrite that. Like these markers, you put them like this, like gravity go to work for about a day. I think will be a good marker for another little bit. So I try to like remember, like I'm done with this marker, I'll leave it like this. Instead of like that, I'll get another day out of it. See? Force times sine theta. This only works when we're measuring theta relative to the horizontal, the positive x-axis, right? So the reason why the vertical component is f sine theta is because this angle is relative to the to the horizontal axis. We've seen situations, right, where there's a block on a ramp and the angle sort of is this way relative to the vertical, and then it changes it, right? Because then it's like the x component, the component going down the ramp, is the sine. So you have to sort of be mindful of where is this angle measured relative to. The force horizontal would be force times cosine theta. I wonder how secure these whiteboards are here. I'll say that for a summer project. Rip these off the wall and leave them up about one cinder block or two. Oh, God. Look at this one here. And then it'll be about here. So I'll go like this. Okay. All right, moving right along. Any questions about that? Resolving the forces into their perpendicular components. So the next one here was define and apply the moment of the force and the torque of a couple. Okay, define and apply the moment of a force and the torque of a couple. Make sure that you have these definitions. I think this is kind of where I made it to, and then like the bell ring. We'll just start to review that. So the definition of moment of force is the force F times the distance to the pivot times the sine of theta, where theta is the angle between the distance, the displacement vector, right? The distance to the pivot and the force. If the force is perpendicular to the pivot, to what we call the lever arm, right? So it's like this is what we call lever, you have leverage, force, leverage. If the force is already perpendicular to it, then the angle between these two vectors is 90 degrees. And the sine of 90 degrees, you can prove to yourself right now, is 1. Take the sine of 90. Okay, it's 1. So it kind of just becomes the more familiar force times distance. Like moment is force times distance to the pivot. Because a lot of the times the forces are perpendicular, it's like a weight that's suspended from it, so weight always goes straight down, so that's going to be perpendicular. We get problems with like the guy walking across the plank, right? And like all the forces were like perpendicular. But sometimes you get a problem like this. Okay, like the force is directed at some angle theta between the displacement and the force vector. And so here, It's really only the perpendicular component of this force. That's what this sort of means. F sine theta is the perpendicular component of the force, the one that's acting in the perpendicular direction to this one here. And so if this angle is the angle theta between them, then you can kind of see that it's really like this vector here, that's the perpendicular component, and that would be opposite this angle theta. But I just kind of drew it over here because it's like, well, it's acting like right there. And so if the force is pointed like this, I'm pushing on it like with all this force, but only the component that's going up right there is active, contributing to the moment. All right. So sometimes we have to be mindful of only the perpendicular component of force contributes to moment. Similarly, when we talk about work on Monday, we're going to remind ourselves that only the component of force that acts in the direction of displacement contributes to work. So torque and work, different things. But they're both the product of force and displacement. So the component of force that acts in the direction of displacement contributes to work. If I push something, okay, an example here. If I push something across this marker tray, and I put all of my force in the direction of displacement, all of that force is contributing to the work I'm doing, the force that I have to exert times the displacement, the distance that I went. But if I push at some angle like this, only the component of this force that's going this way is contributing to work. Some of the force is going just like to push it into the tray, and that's not doing any work. Okay, it's just actually increasing the friction. With this one, if I push on the door, my favorite sort of torque example over there, the torque of the door. If I push on it directly perpendicularly, then all of that force is contributing to the moment of force to open the door. But if I push at some angle, sort of like I'm going that way out the door, so I'll push that way. Maybe that's your hypothesis. That will be better way to open the door. But only the component of my push that sort of moves the hinge is going to contribute to work, right? Like if I push into the door, it's not going to open, right? Let's demonstrate that fast. We don't know what you mean. We gotta see it. To open this door, I just had to like apply a force to it. If I push on the door this way, like we just sort of push on this door, it's not opening, right? You're just like pushing it into the wall. That's not contributing to any torque. The torque is going to be all right. The door handle is far away from the door hinge. Not by accident, right? Because when we maximize the distance to the pivot, the torque to open the door is constant. We can supply minimum force to open the door because there's a lot of distance to the pivot. Much greater force is required here when we try to push the door open very, very close to the hinge. It's possible, but it's tough. So when you've got to open a fire hydrant, okay, you need enough moment of force to be able to open a fire hydrant. Hold on a second. This way. Enough moment to open a fire hydrant. You either have to supply a lot of force, like if you've ever been, hot, and you're like, oh, fire hydrant, let's open that up and try to twist it open. It's not going to work, okay? Because we're probably not strong enough. So you have to generate enough force by just like twisting off of like a bottle cap. You've got to increase your distance to the pivot. How do you do that? You get a wrench. Okay, you put the wrench on the handle, and then now you're applying a force a greater distance away, but it still won't budge. You get a bigger wrench. You say, okay, this wrench ought to do. I'll put this on this cap here. I'll go the greatest distance away from the pivot, and I'll exert the force perpendicular to it, but it still won't budge. You get a bigger wrench. Put that on the end there. You exert force perpendicular to the pivot as hard as you can, still not budging. You're maximizing your force, but you can't generate enough moment to twist that open. So what do? You get a bigger wrench still. Put that on the end there. Try to maximize your distance away. Generate enough moment to open it up. All right, e-learners, I'm going to need everybody to go and get a note from the dean. It's just like skipping, okay, when you just leave like that, all right? And also, I was a little bit late opening up the Zoom call this morning, and so everybody was tardy. So tell the dean that also. I was tardy, and I also left the Zoom meeting inadvertently. That's fair. Okay. We got to hold you guys accountable. All right, so we got moment of force, right? Oh, the biggest wrench, that was the last one. It's longer than all the rest of them. You get it. We'll call ruin my whole wrench act. That's okay. We'll get it next week. How about torque of a couple? Torque of a couple is, what is the torque of a couple? I feel like we need another good textbook definition. Because it kind of helps us think about, the torque of a couple is when we've got identical forces parallel and opposite, right? Let's look at that. The product of one of the forces of a couple and the perpendicular distance between them. The product of one of the forces of a couple and the perpendicular distance between them. So then it kind of makes you want to look up what the couple is. In the physics sense, of course. A pair of equal and anti-parallel forces. Ooh, anti-parallel, I like that. Having a turning effect but no resultant force. Okay. So we'll start here. What's a couple? A couple is a pair of equal and anti-parallel forces. What does that mean, anti-parallel? So it's like this, okay? Like one's going up, like you're turning a steering wheel, and you go like this way with this hand, and this way with this, they're anti-parallel. Okay, they're parallel, but going in opposite directions. All right, that makes sense? So if I want to say turn this wrench, okay, with a couple, I couldn't, say, well, both of my hands are going to go up. It won't work, right? It's like this one's got to go up while this one goes down, right? Or the other one goes down while the other one goes up. That's how you turn something. So that's thinking about anti-parallel. So a couple is a pair of equal and anti-parallel forces. Having a turning effect but no resultant force. Having a, and here's where we go. Having a turning, right? A turning effect. And this will help you remember it. Oh yeah, it has a turning effect. And I wrote the word turning, right? And it's a way to help study maybe. And if in this class you said, wow, that really was helpful. And then you start to use this in geography class to memorize the river that winds, you know, you write it out and you're like, hey, that was actually a very powerful way for me to help memorize things that I need to memorize. That's one of the goals of this class. I mean, once we learn how to think to solve physics problems, there really is a way to train your brain of like how to attack different questions. And it's like, oh, this problem solving, I can apply to more than just like opening up a door. You know, it's like, but who cares if physics, like, so what, you open up the door. And they're like, well, Archimedes said, you know what, give me a place to stand and I will move the earth. That's what he said. And it's like, this leverage is a very powerful idea. And again, used it, Battle of Syracuse, having a turning effect, but no resultant force. And so we're kind of thinking, ahead here to the conditions for an object to be in equilibrium. The resultant force is 0, so there's no net force. The resultant moment is 0. There is no net torque. And it's like that got a little bit cut off there. Okay. So with the torque of a couple, it just turns it. Okay, it produces a turning effect, so it spins, but it's not going to move it to where there's a resultant force. Like when you turn your steering wheel, if it turns it. I remember one time we were on vacation. My wife and I used to go and visit the Bahamas like every summer because her brother-in-law, lived there, and so we could, go there. So it's really cheap, it's like fly right in, live on a Navy base. And we rode around in golf carts, everywhere there, because it's just like a little sort of 1 mile square sort of base there. And my wife one time, it's like, like you turn the wheel of the golf cart, but she kind of like used it to kind of pull herself up in the seat a little bit and pulled the steering wheel like right out of the thing. Like it popped right onto there. It's like we're driving, and it's like, oh, I don't have a steering wheel anymore. So it's like, you can't think that far. It's like almost like there's something to face with that. While we were trying to have a turning effect, like I move this thing, right? It like ended up with a resultant force and pulled the whole steering wheel off. Like that's not what you want to do, right? So like you're a pilot sitting down at your aircraft, and you have your controls here, and it's like, okay, we need to sort of bank the aircraft this way, and instead you pull the whole thing off. It's like, oh no, that was a resultant force. I didn't like the turning effect there. Okay, so it produces a turning effect. That's what a couple is. A pair of equal and parallel forces having a turning effect with no resultant force. The torque of a couple the product of one of the forces. So the couple is the pair of forces. The torque of a couple is calculated like this. One of the forces times the perpendicular distance between them. So you've got a steering wheel. Right? And those are our anti-parallel forces. They're a couple. They're equal, so they have the same value. Okay? The perpendicular distance between them is going to be this. In order to calculate torque of a couple, it is one of the forces times the perpendicular distance between them. Right? So this is. Okay. If you did force times radius, and you thought like, okay, the center of my circle here is kind of like a pivot, and I thought about it like moment of force, and you did force times r, the radius, that wouldn't give you the torque of a couple, right? Because it's one of the forces times the entire distance. But if you thought, well, I've got force times r, and I've got another identical force times r, so if you just doubled that, right? Like if you think about this is the diameter of this circle, and so we know like half of it, right, is the radius. These are really kind of saying the same thing, aren't they? Okay, that the way we calculate moment is force times distance to the pivot, where like we could call this r if we wanted to, like it's the radius if we made this thing go sweep out a whole circle. So think about torque of a couple as one of the forces, because there's always going to be those equal and anti-parallel forces in our couple. This one of them times the entire distance between them. In other words, instead of like doubling the moment of one of them, we double the distance. It's mathematically the same, okay? So torque of a couple, let's sort of put it in there. The product of one of the forces of a couple, torque of a couple. The product of one of the forces of a couple and the perpendicular distance between them. The product of one of the forces of a couple and the perpendicular distance between them. The perpendicular distance between them, this, one of the forces, F, right? So that kind of worked out nice the way I had that figured out. And it is helpful to think about like moment of a force with a figure like this, torque of a couple with a figure like this. As I alluded to earlier, the fifth learning, now the fourth one is about applying the principle of moment. So I learned about moment of force. That will take a little bit longer to review, and so I sort of, dedicated the whole real estate of the other chalkboard to that one. This one we can sum up in these two sentences. Just something you got to know. I've seen a lot of paper 2 questions which say, state what is meant by, an object to be in equilibrium. What are the conditions necessary, for an object to be in equilibrium? So there are 2 conditions. One of them has to do with all this stuff. There's no net torque. There's no net moment. The resultant moment is 0 for an object in equilibrium. If there were a net moment, what's going to happen to it? It's going to spin in that direction where the net moment is. Okay. If there's enough friction between that fire hydrant bolt, that even when I exert a force on it, it doesn't move, then those forces are balanced, right? So I could exert a tremendous moment, but then there's friction there that's equaling sort of that moment. So that would be in equilibrium because there would be no net torque or no net moment. Also, it can't be accelerating, right? We know that if there is a net force, it will accelerate according to Newton's second law. So an object that's accelerating is not in equilibrium. Okay. The resultant force also has to be 0. So the easy way to kind of think about it is no net force, no net torque. What's the conditions for an object in equilibrium? No net force, no net torque. Okay. More formally stated, the resultant force is 0, the resultant moment is 0. Right, and then finally we've got apply the principle of moments for an object in equilibrium. Apply the principle of moments. For an object in equilibrium, the sum of the clockwise moments equals the sum of the anti-clockwise moments. So that is the principle of moments. Principle of moments says for an object that's in equilibrium, the sum of the clockwise moments equals the sum of the anti-clockwise moments. Specific to like that second condition. Okay? It's possible that an object could have no net moment. Okay, the resultant moment is 0. In other words, this is going to be true. The sum of the clockwise is equal to the sum of the anti-clockwise. And yet it's not in equilibrium because there might be a net force acting on it. So keep that in mind. Like the full-blown sort of conditions for equilibrium are no net force, no net torque. And usually we're sort of considering either an object with like a translational force that's going to make it move, right? That's going to sort of be a result force that's going to make it accelerate. Or we're considering like moments acting about a pivot. And we're not really worried about the thing moving sort of translationally in space, left or right, up or down, just like it's going to twist or turn or something or rotate. So it really would be more complete to say, for an object with no resultant force, it's in equilibrium, like in that regard also, then this is true. Because it could be that, hey, there's just no net moment on it, like this flag here has weight at the end of it. The weight of that is exerting a greater, moment about that pivot than like the parts of it that are closer to it, okay? And so right now it's in equilibrium in terms of both of those conditions. There's no net force, it's not accelerating, there's no net moment. So like the moment from that is equal by the friction in the pivot down here, right? Like that support right there provides enough anti-clockwise moment. So like the clockwise moment this way, would that be clockwise? I guess that's the anti-clockwise moment. Provides enough clockwise moment sort of the other way, okay, to sort of keep it there. That could still be true, and the whole wall could collapse, right? It would accelerate down. So it's like, okay, there's no net moment, and yet it's not in equilibrium because there could be some net force. You know, like its weight makes the thing collapse. So just be sort of very careful with this. A flagpole of mass 25 grams is held in a horizontal position by a cable. So a flagpole held in a horizontal position by a cable. Okay. The mass of our flagpole is 25, what is it, kilograms? 25 kilograms. All right. The center of gravity of the flagpole is at a distance 1.5 meters from the fixed end. Okay. So it is sort of a flagpole that kind of goes like tapered. Okay, it's not uniform. If it's a uniform rod, a uniform board, a uniform plank, whatever, then we know that its center of gravity is in the center. Here, it's not, okay, but they tell us that its center of gravity is 1.5 meters from this fixed end. So 1.5 meters to get to that point, which is the center of gravity, the point where all of the weight could be thought to act. Okay? So keep that in mind. We're given the mass, but we're talking about forces, moment of force. And so we say, well, if it has mass, it's in a gravity field, it's got weight, and I can calculate it. I know the gravity field strength. We can assume this is a flagpole here on Earth. Unless they tell us otherwise. This is a Martian flag, you know. Write an equation to represent taking moments about the left-hand end of the flagpole. Use your equation to find the tension T in the cable. So you've got a flagpole. We want to calculate the tension T. Any thoughts? Where should we begin? Well, lots of time left. Oh no, not a lot of time left. It's not Wacky Wednesday, it's Freaky Friday. Where they just ring the bells at any time they want to. There's no rhyme or reason to it. So we might be dismissed in 5 minutes, it might be 30 seconds from now, who knows? Oh wait, no, they publish this schedule. On Friday, we get out of here at 9:49. So maybe 10 minutes from now. Plenty of time, all right? But not if we can't make some progress on this. Watch this. Applying a force a distance away from a hinge. Yes, I will. We're going over moment of force.
Oh my goodness.
Yeah, you have to have like sometimes I struggle with that every morning also.
It's like a mess. Hi, Dr. Sly, how are you?
Pretty good. We're just talking about moment of force and opening up the door, and I was using that as a teachable moment. I said, so watch this, a force is going to be exerted a distance away from a pivot, and the door will open, and then I'm like, Or maybe not, I'll go.
I was a force coming through. I came down this morning to get the light stuff. I came in this morning and got it, but I'm missing a cord.
Okay.
Let me see if I can find it.
All right, let's get back to the calculation at hand here. So we want to use this law, obviously, right? This is kind of why it's over here on the chalkboard. We're applying the principle of moments. This object is in equilibrium because it's not rotating, right? Like we're keeping up. This is called guy wire, not a guide wire, a guy, G-U-Y, guy wire. And so let's calculate the clockwise moments, okay? There's only one thing that would produce a clockwise moment, and that is the weight of the actual flagpole itself, all right? What is a sensible point to take pivots about? Oh, the other thing that's, I guess,
Force is leaving.
how we going? I suppose the other sort of critical piece of information, I was wondering, can it tell us that whole thing is 2.5 meters. So there's really only two forces. There's the tension and there's the weight. The clockwise moment is from the weight, right? If this guy wire weren't there, then the weight of this flagpole would make it go like this, clockwise, all right? So let's calculate the sum of the clockwise moments is just this, all right? So how do we calculate moment? So I'll do clockwise moments. I kind of like to use this kind of symbol, like this turning effect, okay? So the clockwise moment equals the force, which is weight, times the distance, which is 1.5 meters. Right? The weight acts 1.5 meters away. That's what center of gravity means. It gives us the center of gravity, the point where the center of gravity is. The mass is given, so I got 25 kilograms times 9.81 newtons per kilogram times 1.5 meters. Newton meters are the units of moment, not joules though. Don't ever talk about a joule of moment. Even though with work, a Newton meter is a joule, we never say that that's equal when we're talking about moment. We always leave it as a Newton meter. Okay, you just have to kind of know that. What is 25 times 9.81 times 1.5? 250 divided by 1.5. What do you get? 170 something, maybe? I don't know. I have no idea. What is the clockwise moment from the weight? 25 times 9.81 times 1.5.
367.9.
Yeah, I was way off. Say it again.
367.9.
Anybody else getting that? Good. Newton meters, right? Now we're going to set it equal to the anti-clockwise moments. The anti-clockwise moment comes from the tension, right? The tension is sort of secured here at the end. But think about it like this now. The other critical piece of information that I didn't give you. This makes an angle 30 degrees. Oh, if you would have told us that at first, you'd have a better idea how to approach this calculation. Give us the angle. We could calculate the the perpendicular component. Okay, the perpendicular component. All these learning objectives related to each other. Direction of, oh, that's precariously situated. What's that? Bells on the ring, but we gotta go on in this calculation. Only the vertical component is going to contribute to the moment, okay? So the tension actually exists everywhere in the wire, but only this component of it is balancing out the moment here, okay? So We can either think about this as the side opposite this 30-degree angle, right? Like I could resolve this vector and say, well, there's a component that goes like this way, and there's a component that goes up. And the up component is really acting right here, 2.5 meters away. Like that's my distance that I'm going to plug into the moment. But I could sort of resolve it over here, mathematically, just thinking, oh, it's opposite this, the one that I was given. Or it's adjacent to this 60-degree angle right here, right? If you prefer to work with it over here, like, oh, it's actually acting right here. I'd rather just take the cosine of 60 times t. So it's either cosine 60 t, or it's sine 30 t. That's the component, that's the force that goes in for the anti-clockwise moment. So now we have the anti-clockwise moment, force times distance. The force is, I'm going to use sine 30 degrees t times the distance, all 2.5 meters, right? It's acting all 2.5 meters away from the wall. There's our equation to solve for t, right? T is the only unknown now. We know the left side because we're given everything to calculate the moment. We know the distance there, and I prefer to kind of work with the angle given. So it's easy enough for me to go, okay, well, that's the same thing as this one, but if you prefer to use cosine 60t, your calculator won't have any trouble, showing that that's the same thing. All right, so divide each side by 2.5, and then divide each side by the sine of 30, and then you would have solved for t, right? So 367.9. 367.9 divided by 2.5. So remember, this is a Newton meter, so when we divide it by 2.5 meters, we're in newtons. And I get 147, and then divided by the sine of 30 is a half. So the tension is 294.32 newtons. Okay? That's the actual tension in the string. Only sine 30, only half of that, okay, is actually contributing to the anti-clockwise moment. The total tension in the string is T. It's like actually here in this vector going this way. But we have to realize that because the definition of moment of force is the perpendicular component contributes to moment, we have to include that sine 30 there. And this is like a very typical kind of physics problem where we got to remember that angle. Remember we said there's a lot of problems where like it's always going to be perpendicular, like a weight acting straight down like this. And we have to take an angle with this one. But if it's a guy wire, it's just connected to this building, right? It's always going to be at an angle. And then we got to use our trigonometry. Okay. So this is sort of the more typical example where we really need this whole form of that equation where we're mindful of the sine theta. Any questions about applying the principle of moments in the 30 seconds before the bell rings? All right. Pause that.